introduction to fuzzy nonlinear optimization. So, as we know that optimization is one of the important uh, thing or phenomena, okay, which always comes in and around us, starting from the morning when we wake up till night, whatever we think, we decide, we do. So there a bit of optimization we have. Okay, always we try to do our work with less effort, and the output should be uh, sorry, and the output should be the best. That should be the idea behind whatever activity we do. So optimization is very important. In that optimization, we have different categories. We will discuss through what are the categories, linear, non-linear, and based on the objective function, based on the constraints, what are the types of optimization problem we get. And after that, the main part is whatever we do in our day-to-day life, okay, in the physical world, we have as some sort of uncertainty come across. Okay, and that's uncertainty, maybe different type of uncertainty that also we will going to see. So a particular type of uncertainty we have that is called fuzzy. So we will discuss that. So when we have a linear nonlinear optimization problem with fuzziness or the parametric form is fuzzy, then how do we tackle that problem and arrive at a uh, approximate confined solution which will help us to take a decision. So based on that we are going to discuss. I have to present my talk based on that. So as we have talked about uncertainties, so uncertainties we have different type of uncertainties due to the occurrence or the cause. We have different type of uncertainties. So first we have the measurement error. Sometime we do mechanical or measurement error, due to that some uncertainties come. Then next we have the type is impreciseness, when we don't have any precise knowledge, precise value of a certain thing. Impreciseness. Then due to randomness of a value or parameter, due to vagueness and lack of information. When we don't have sufficient information, we assume and we believe something, and we, based on that we take the value. And then the outliers are the data set which validate the data set. Sometimes outlier is like 1 out of 100. Okay, if we ignore also, it is not affecting the solution, and sometime it validates the data set. So that also plays an important role. Uncertainties, as an uncertainty, data insufficiency also plays a role. So these are the form of uncertainties. Now if we divide basically in important or major two way we can define, that is aleatory uh, uncertainties. Another is epistemic, which popularly we use. Aleatory is due to randomness, and we handle through probabilistic statistic axioms and rules. And the impreciseness, and that we use interval or fuzzy set theory to tackle those type of data or the uncertainties. So here we have interval or fuzzy set theory that I will bring light on this. Okay, so the fuzzy set theory will start with a simple definition of fuzzy set theory. As I believe that you have already been through that. So we fuzzy set is nothing but the order pair. So this x comma mu x, so x is the element and its membership function. Membership function belongs to 0 1. Okay, but in a classical set theory the membership belongs to 0 or 1, yes or no type. So in that if a fuzzy set satisfy three property, that is continuous, means piecewise continuous, convex and normalized fuzzy set, then it becomes fuzzy number, and there are different type of fuzzy number. One of the type is triangular fuzzy number. We have three values, AL, AM, and AR. So AL is the left value of that fuzzy set or fuzzy number, and AR is the right value, and AM is the center value. Center value means at AM the membership value is 1, and AL is membership value 0, but the left value, AR is the membership value 0, but the right value, and the membership function is defined like this, where mu L is a linear function which is non-decreasing function. Mu R is another linear function which is non-increasing function. Okay, like that we have other form also. Now if you want to see a fuzzy number, we can define through uh, one parametric form, means we can introduce one parameter and we can convert this into interval form, and that form is this AL to AM. There is a piecewise piecewise continuous function. So what we can write, AL plus AM minus AL into alpha. Okay, alpha is nothing but the value, parametric value belongs to 0 to 1. And the right function we can write AR minus AM into alpha. This way we can write in the parametric form. There are different type of fuzzy numbers. We have that already we discussed just now, the TFN. Similarly, TRFN, based on the uh, function distribution, based on the membership function distribution, the name is coming. Here it is looking like trapezoidal. Okay, that's why it is TRFN. So from this to this means here you can see the value of membership value is 1, means from this to this x value we have membership value 1. Here at one point it is coming normalized, but here we may get an interval for that. So that is TRFN. Similarly, Gaussian fuzzy number will be looking like Gauss function. So that's why the distribution looks like Gaussian function. The distribution means here the membership value, okay, how it comes, based on that we have Gaussian fuzzy number. So these are the different uh, terminologies that we are going to use. Okay. Now, before going to discuss the thing computationally, let us see why that is so need of the uh, optimization. Understood? Now, through is it visible? Okay. So now what we have, we can take one system of equation. Let us take like that. uh, Interval system of equation. So if I take interval system of equation, so what is that? Means ax equal to b. So we'll see the simplest form. For example, it is 2 comma 5. So 2 comma 5 is the interval, and here we will multiply with x. That will give, for example, 4 comma 10. Simple. Now here what we have different way of solving, okay, as we know, but the correct way is by applying interval technique, interval arithmetic. So people are doing in different way, like left left means here if you multiply first equation we will get 2x equal to 4. That means x equal to 2. Here we are getting x equal to 2. Another is right. If I do right, then what happens? 5x equal to 10. That means x equal to 2. So if you change it to 4 comma 15, for example, if I change, then this becomes 5x equal to 15, that means x equal to 3. So in this case, first case, what we can get, the interval x as 2 comma 2, and another case x we are getting 2 comma 3. This is one form people are doing, that may not be correct always. So another case is by taking left to right. If I take left right, so x we will get 10 by 2, okay, so 5. Another x we are getting 4 by 5, okay. Now 4 by 5 we are getting here. So this time we can take that x value is 4 by 5 minus 5 is the interval. Now we can see that this interval has more width. Width is what? Width is xr minus xl. Okay. You can take modulus. If you take modulus, if you change also xl, xr, no problem. But the thing is that this is the width we are getting. Now here you can see width is more, here width is less. This 2 comma 2 is nothing but 2 also you can write. So here width is 0. So this is another form people are doing. But the main part is when you solve system of equation, 2 by 2 system. Let us see, I will take one 2 by 2 system that will be useful to do here. 2 cross 2, sorry, 2 cross 2 system we will take. That means if I take A matrix as you can take 2 comma 5, for example here 2 comma 5, okay, here 3 comma 6 you can take, then here 1 comma 8 you can take, here 3 comma 10 you can take, like that. So if we have this as interval matrix, then, and B you can take anything, B also you can take, for example 1 2, okay, and 3 4 you can take, okay. So if you take like this, so this is a matrix. Now what we have in Ax equal to B, the solution will be A inverse A x equal to A inverse B, and finally we can get x equal to A inverse B is the solution. Now the thing is that how to find A inverse. Now in this case the problem is that in this A matrix we have certain things which will violate the rule to make A inverse. For example, if I write there is a combination in between we have, or there are infinitely many combination of values you can take, but out of that if I take A as 4 here 4, all 4, if I take the element, okay, what happens? It's A inverse not exist, okay, not exist, because the determinant of A is 0, okay, determinant of A is 0. So in that case how do we get the value? How do we compute A inverse? So that is a big problem. So direct method finding the A inverse is difficult. That's why to get x value in interval form it will be difficult, because there are infinitely many combinations in this. We can see which makes the matrix singular. So in that case optimization can help, because if we convert this problem into an objective function, then we can find out the best solution of the uh, find out the best solution of the objective function, and that will help us to get the precise solution. We may not go through the usual inverse approach. We can avoid that and we can get the solution. That is what the optimization approach. Okay. Now, when I talk about optimization, then this optimization will have different type. What different type? One is called linear optimization. Linear optimization, that already may you know that LPP is one example of linear optimization, that is linear programming problem. Another is called your NLPP, that is nonlinear programming problem, or if I write, this comes under what? Nonlinear. So one is linear optimization, another is nonlinear optimization. Again, the optimization problem that we can define in two ways. One is single variable, okay. That means if I have a function f of x only, that type of function we have, and constant may also we have in terms of a single variable. Another is multivariable. Like if we take two variable function, so f of xy, and if we generalize n number of variable may come, depending on the problem we may have values. Okay. Now the question is that then how do we solve ax equal to b? What is the technique? How we will convert to optimization problem? So here again I want to tell you that the optimization problem OP can also be defined or divided as your inequality, equality, unconstant form. One is unconstant form. Unconstrained form. Unconstrained form means we don't have any constraints. Another is equality constant. The last one is inequality constant. So we will discuss about the unconstant form. We can convert this optimization problem to unconstant optimization problem form, and then we can find out the optimal solution. That optimal solution is nothing but our x value, the field variable that we are using or that we are going to find. Okay. So one by one we are going to discuss. So now here we understand the classification of optimization. Next, move on to one application, then we will see further things. So the architecture of the problem, first we will see what optimization we have in that. So when we deal with physical problem or real world problem, then we have many parameters, values. Okay, we have different values, different parameters. Now what we do with that? First we first we do the mathematical modeling to get the field variables. Okay, so here we are going to discuss one spring mass problem. Through that I will try to make you understand how we convert that problem into our optimization problem with incorporating the fuzzy, and then how to solve. So through mathematical modeling, we can either convert it into one of the algebraic form, that is linear system of equation, nonlinear system of equations, then eigenvalue problems we can convert it into, and the last is complex system of equation also we can form, depending on the behavior parameter and environment of the problem. Different type of algebraic forms we can get. Now from the algebraic forms, what we can see, we see there are some parameter which are uncertain due to fuzziness or other means, but we are going to discuss about the fuzziness. So one by one we'll see, and through that uncertainty we can convert it into optimization problem, or just now what I have told you, that unconstant optimization problem. And after getting the unconstant optimization problem, what we will do, we will apply the proposed optimization algorithm what you can developed, or maybe whatever it is exist, that also you can apply and get the optimal solution. And that optimal solution will give a approximate or the local behavior or the field variables in fuzziness or whatever uncertainty you are defining based on that. Okay. Now here, try to understand, see what we have here. Here we have discussed a spring mass problem, and you can see there is a car. So if you have seen in our in roads, we experience jerks. Okay, so when you travel with two-wheeler, four-wheeler, okay, any other, so you feel a jerk when the roads are rough, okay, not even. Then what happens, the jerks can be balanced through spring. Okay, means actual jerk what you may experience, that will reduce if you have a suspension or proper suspension in your vehicle. That suspension is nothing but the spring mass system. So what it makes, the when you drive your car, when you exert a force, that force get damped, and the force, direct force, when it reach to you, you feel less um, exert, because the force somewhat get reduced or damped. Okay, so that system when we discuss, that is nothing but the simple that already we have seen in the very beginning intermediate level, that is spring mass problem. Now you can see that this is the design of car. In that there are spring constant K, okay, that experience due to force, and there is a damping C. Okay, and the force, when force exert it, if the force is in the top direction above to the car, okay, means when you get force from the back below, it will exert towards up. Okay, and x is the distance that will cover when you drive from one point to another point. So through that you experience a force. Now the force, if we take that force is uneven force, because the road where we are driving, that is rough. Rough means uneven force will occur. So uneven force will occur means, can we tell exactly precisely that what force we will get at what point? No. So what we can take, that force we can take as fuzzy, because these are imprecise in value, or we can take that force as uh, in terms of interval. Okay, by taking that into our knowledge, the car is designed, or the vehicle is designed so that in a particular range of force we will get less exert, or we will get less jerk. Okay, and we know that beyond some interval, that everybody will have a breaking point. Okay, so we get a range of f. Okay, now that if I take that force as input and in terms of TFN. That means TFN means what? This is the X force, and as per X, the membership value is varying. Okay, that means the chance of here, if I see 2 at this point and this graph I can see, that means at 2 when the force is 2 Newton or some variable, okay, depending on that we are calculating the force. So at 2, when it will be at 2, then most of the time we get the jerk. When we are at 0, the most of the time the force, jerk force is 0. Here jerk is 5. This way you can take, or either the force also you can take 0 to 5 Newton force, for example 0 to 5 Newton force. Okay, so there is obvious that most of the time we are getting 2 Newton force. Rest of the time 0 to 5 how it is varying. Okay, similarly you can take it as in TRFN also. When you want, for example, you are moving from one place to another place and see that for a particular period of time this force you are exerting, okay, means you are going through highway, for example, most of the part is highway, so you will get smooth surface, so force is less, otherwise force is more. So those are the cases where you can figure it out, that the force is in how it will behave based on that different type of fuzzy input you can take, fuzzy force you can take, so that your model will give a better solution to understand the behavior of your vehicle or the hydraulic system, or the how it will force the feel the suspension, those things. Now what does it happen? These are the parametric values that undergo the operation, what we do the algorithm through the all the algorithm, the parametric values propagate, and after propagation of the parametric value we get a set of solution. Out of that, the set of solution, the optimal solution that we get, and that will also comes as fuzzy. So here one question may arise, that can we have always a fuzzy output as TFN when we take TFN input? The answer is no. But why then you have taken fuzzy output as TFN with TFN and TRFN, TRFN? This is just the approximation to visualize the solution. In general, when we do the computation, yes, depending on the alpha value, membership value, this output changes, the shape changes. But what we can do a list, or when we can try to fit that set of solution, and if we fit through straight line we can get a TFN, because what we have, all the solutions are uncertain in nature. So to get a precise knowledge about the uncertainty, we can make a best fitting. So linear fitting of the uncertain solution we can do, and we can get a TFN, we can get a TRFN. Okay, that may be very helpful to visualize the solution. So this is the entire mechanism, okay, how we can apply. Next we will go through the technique what we use, that is the hidden layer what we do. Okay, so this is a spring mass problem that we have discussed. This is the modeled equation for a spring mass problem. M is the mass matrix, C is the damping matrix, K is the stiffness matrix, F is force. And we want to find out this X as displacement. Now X double bar is acceleration, and X is your distance that we are going to find. So mass matrix we can find out for M system, N cross N system, or N story building, what we can call fine. So M will be a N cross N matrix, mass matrix. Then similarly the damping matrix and stiffness matrix, all three you can get. And the force will be, there are N components in the force. Now, by converting that problem into algebraic form, you can get this m lambda square plus c lambda plus kx equal to 0. Here lambda is the eigenvalue. Eigenvalue depends because eigenvalue is a major part in the structural problem because eigenvalue gives the frequency, and based on that we can understand the jerkness. Okay, so when you take the uncertainty involved in the mass matrix and damping matrix, stiffness matrix as fuzzy, so it becomes like tilde we represent to do that. So here you can see that, and after converting the TFN into alpha cut form, we will get one interval that I have shown you how we can convert. So here it is a mass matrix in terms of fuzzy, which is converted into interval form, then damping matrix, stiffness matrix, and when we solve the problem, we get this algebraic system, that is, here we can talk about Ax equal to lambda Bx form. Okay, now all in fuzzy form. Now what we have then, how to solve this problem? So we arrive at here Ax equal to lambda Bx. Now we will go to the technical part, that is how to solve them. Okay, so I will show you here very basic thing how we can do that. Okay, for example, we will see a standard system Ax equal to b. Now Ax equal to b, here what we can write, a we can write as a11, a12, a21, a22. A small case I am talking, you can generalize this concept. Okay, b vector as b1 and b2 you can write. Now how do we solve this problem? So we will solve this problem through optimization technique. So we will convert this into unconstant optimization problem. How? We will see. So Ax equal to b, that means what we can write, and this system if you write, so it will be, first equation is a11 x1. Here x vector I have to write, so x is nothing but x1 x2. Okay, I'm just giving you the idea in crisp case. Okay, here a11, a12, a21, a22 all are fuzzy number, b1, b2 also fuzzy number. So if you want to expand it, it will be a11 x1 plus a12 x2 equal to b1, then a21 x1 plus a22 x2 equal to b2, this form. Now this, what we can write, this first equation again we can write a11 x1 minus, sorry, plus a12 x2 minus b1 equal to 0. Fine. Then second equation we can write a21 x1 plus a22 x2 minus b2 we can write equal to 0. So 0, 0. So what next we can do? We can do like this. So we can write 0 plus 0 equal to 0. Yes, correct. Can we write 0 square plus 0 square equal to 0? Yes, this is also right. Now this is the idea what we can write. So these two equation we can merge and we can write a11 x1 plus a12 x2 minus b1 whole square. Okay, plus a21 x1 plus a22 x2 minus b2 equal square equal to 0. Yes, now this, if you see this, I can write as a function f of x1 comma x2. Yes or no? Yes. So we got f of x1 comma x2 is 0. Now this problem, finding out the solution, so what is then x1, what is then x2? This is nothing but, if I solve the problem, minimize f of x1 comma x2. So this is the optimization problem. Okay, so finding out the solution. But here one Big advantage is that the minimum of squared function is 0. Okay, that means already we know the solution minimum of this f of x1 comma x2 tends to 0. That means whatever investigation we do, if the algorithm we are doing, putting, and finally if the function value converges to 0, then we can get confidence on the algorithm, that algorithm giving correct result, or it is the approach is correct. Okay, so that idea. So this is nothing but the problem statement of unconstant optimization problem. Here it involves the coefficient a11, a12, b1, a21, a22, b2, all are fuzzy. That's why it is called fuzzy unconstrained optimization problem. Okay, so this is the problem formulation. Now what we have seen? We have seen a physical problem where uncertainty occurs, then how we can convert it into fuzzy unconstrained optimization problem. Means by using the numerical method, we can convert the differential equation. Here what we are doing, we are converting the differential equation to algebraic equation, and then we are applying FUOP. Okay, and that solution, how we will apply, what technique we will apply through and solve, and we will get the solution that we will see. Now in that we have developed one algorithm that will handle easily, that is inner outer optimization technique, that we will see. Here I will show you inner outer method. So inner outer, okay, IODS method, 1 minute. Yes, IODS or inner outer direct search method. There are different type of search. Okay, here what we have, here we have direct search. Okay, another is called indirect search. So what do you mean by direct search and what do you mean by indirect search? Direct search is when you search along the axis. It is basically called direct search. When you search through other means, then it is called indirect search. One of the example for other means is gradient search. So here our point of discussion is to search it through direct way. Okay, so I will show you a little bit idea IODS technique, and why we are not going through indirect search, that also I will tell. So direct search means when we take 2D, okay, 2D problem. For example, this is our initial point and we were searching our solution. Somewhere we have solution that we don't know. So how do we approach if we have two variable, that is one is x1, another is x2 variable, because just now we saw that function f is x1 comma x2, so we have to search in x1 and x2 direction. So what we will do, if this is the starting point, so first we will explore through x1, then we will explore through x2. For example, this is delta distance, so delta distance towards right we will go. Okay, then delta distance towards left we will go. For example, if we have a point x1 and okay, just write xy. Okay, now first is what, we will take x plus delta comma y, one point. Another we will take x minus delta comma y. So we have to find out the function value at this 2 point, and we will see which one is minimum, which one is minimum out of this, that we will discuss, that we will tell. For example, this value is minimum. If we compare these two, then we will fix this point. Then from this point, what we will do, we will move up, we will move down again delta value. So what will be the next value, next point? Then here I will write, so it will be x plus delta already fixed. We are exploring y direction, or we are exploring x2 direction here. This here I have written in xy form, but here it is x1 x2 direction we are doing. So x plus y, then 2 point y minus delta is 1 point. This is f, and f of x plus delta, y plus delta. So this 2 point we have. So at this 2 point again we will find out the search. For example, for this point we will get minimum. So here we are getting the updated value after exploring in two different direction, x1 and x2. So depending on the multivariable function, you have the variables, number of variables you have to vary in that, okay, a number of variable times. After getting that, what we do, this is called, what we have, the exploration move or exploration search, exploratory search. And then what we do, we find out a pattern. Means from this to this we got this point. So how to get pattern? So if this is point P1 and this is now point P2, so we will do one another pattern, that from this to this we will put a line and point P3. So what is that line? Line is the reflection of P1 through P2 is P3. So we will reach at P3. So P3 is the point. So this complete one iteration. Okay. So one exploration, explore, and one pattern. Like that, we have to get point. Then again, we have to search this or this. For example, this is a point, then this or this is the point. Then again we have to find the reflection. For example, here is the point. So like that we need to search. Now the thing is that there are some cases where the minimum point is what we are getting, that is more than the previous point. Means previous point we got minimum value is better. Okay, then what we can do, reduce the size, this delta size, step length, we can reduce and find out our next best point. So this is the approach through which we can go and do. Now why IODS is better? IODS is better than your gradient, in that sense that in gradient we have a chance that when we take interval or fuzzy, we may arrive at some point where we will get a singular matrix. Singular matrix means then operation may not be possible, Jacobian and other things. Finding Hessian matrix will be difficult. So in that sense, IODS will be better. But when there will be uh, high nonlinearity, then maybe the IODS algorithm immaturely converges. Okay, so that is one disadvantage, and sometime it will take a lot of time. So time cost is more than the gradient. So there are some advantage, there are some disadvantage if you compare with other indirect method. This is one of the technique that we have used here to tackle those things. Now briefly I will discuss through uncertainty what we can do. So first we convert the system into fuzzy unconstant multivariable optimization problem that I have told you. Then we will calculate inner, outer, center, because each fuzzy can be converted into double parametric or two parametric form. Okay, if you take type 2 also, you can get there three parameter will come. So type n n plus one parameter you need to do. So it is a generalization process. You can do that. Okay. So as number of variable, number of uh, your alpha values are there, means if a multivariable function will have two variables and one fuzzy value you have taken, that means you will get three parameters. If you are doing in terms of interval and inner outer direct search, or if you want to convert to crisp form and you do, there are four parameters will come in multivariable problem, and all those things will optimized. So that is the beauty of getting optimization. So there may not be your coming across the singularity. Okay, so what we do, choose initial variable, initial value x naught, variable increment delta I that we have discussed. Why I? Because whenever your updated value is more than the previous values, then we can decrease the increment so that the local search can be done effectively. So that way we can do. And as I have told that we are adding delta value, subtracting delta value, we can define that f plus, f minus, and all the time we are taking minimum. So this operation we need to do, and the number of times you do, and the stopping criteria we will get x is not equal to xc, current value. So those things, then pattern search, what I have told, that pattern search you need to perform. After performing pattern search, then this is one of the stopping criteria, because as it is a numerical technique, you have to stop at some point. When your delta value is too small, you can stop at that point and you can find out the uh, mean value of, or average value, you can get it as a solution. Okay, so this way we can do. This is our pattern search formulation, that how you can find out the reflection of previous point through your current point to get the next point. Okay, these are the theorems that will support to the algorithm. You can go through my paper, there you can get it. I have given that paper in the reference link, reference, or you can go through my Google Scholar or your Scopus database. You can get this problem. This is published in uh, your Matcom journal and AIMS Mathematics journal. So there you can go through. Okay. Now different cases we have taken. If we take a different cases here, the plus point is that you need to do this calculation, 7 calculations you need to do. Out of that, minimum maximum you can find, and that minimum maximum will give you the interval value, and we can find out the width. Now if this is the solution and taking the minimum maximum, you can see that iteration wise how we are investigating. This is one problem in case 1 we are discussing. Case 1, case 2, case 3 are nothing but the case when we are talking about system of equation. Right side vector is fuzzy, left side coefficient matrix is fuzzy. This is case 2. Case 3 is when both are fuzzy. Okay, now we can see the width is converging nicely, so that will validate our algorithm. So this way we have found out. Here you can see the solution what we have in TFN form. The x1 and x2, we have x1 in red color, x2 in blue color. Then width wise how it is converging after few points of iteration that is showing. So similarly, when coefficient matrix we have taken fuzzy for the mentioned problem, we will get this solution. Okay. Now here widths are less, that's why you can see the triangles are very thin triangles. Case 3, when both the coefficient matrix right side vector is fuzzy, so this case you will experience more uncertainty. So you can see the triangle, you can understand. Right side 21 figure nicely converging. This is the problem 2 we have taken here. There is 3 cross 3 matrix. Okay, 3 equations are there, 3 unknowns are there. It is again a nonlinear system because here it involve x square term. So we have taken the initial point here, initial point we have taken 111, step length is 0 0.5, 0 0.5, 0 0.5, epsilon value means the delta, this norm, delta norm we are taking 10 to the minus 4, then we will stop if less than that. Okay, so this, the values of A11, A12, all those things are in alpha cut form is given, you can see. Okay, so using that we can find out the solution. Now here you can see, here the coefficient matrix is fuzzy only because the right side vector is crisp values. So this is the case 1 here we have taken, and we got the solution. It is nicely converging at 13 iteration. So we will get the solution. Solution is what? 1.4983 comma 2.9104 in interval form. Okay. Similarly, x2 we can find out, x3 we can find out, and this is the solution in figure 22. 23 will give the convergence of solution, how nicely it is converging after fourth iteration. Slowly it is converging, but after fourth iteration the convergence is very fast. Okay, case 2 where you can see x1 tilde, x2 tilde, x3 tilde we have taken, means the right side vector is fuzzy. Okay, and 24 gives the solution of x1, x2, x3, whereas 25 gives the width convergence, which validate our method. So x1, x2, x3, all three components we can get. In case 3, both the coefficient matrix and x1, x2, x3, that force vector we have taken fuzzy, and we can find out the solution. Here you can see gradually the width increases. Means when you take uncertainty, when you take uncertain, more uncertain parameters, so definitely the uncertainty will increase. Okay. So that's what we are getting, and this is another problem where we have compared with various methods, and also that also find nicely. So we conclude that for GIODS method is, we can tell one of the reliable method. We can um, more or less approximately predict the solution where it will lies. Okay, so for the that problem we get the fuzzy solution like this. Okay, so that's what we have here, and we saw that how the a problem comes from physical world problem to fuzzy problem, and then how optimization can be applied, what is the physical system where the fuzziness comes, how do we incorporate, and what technique we can use, means fuzzy technique, fuzzy optimization techniques to get the solution. There are plenty of research going on in this area to find out better solution, to predict better way the uncertainties and the outcomes or solution. Okay, there are various indirect search method like Armijo and other line search also people used to take, and they can improvise the solution. There are two things we can improvise, that either the solution reach fast, means the convergence rate is good, otherwise second thing we can see that how close we can get the exact solution. These two, uh, taking the idea of these two or keeping this in mind, we can develop different techniques, or we can use available techniques. Okay, so these are the references you can explore, and a few references only I have given here due to limitation of the slides. You can take more also. You can search my profile. You will find plenty of papers are there which will help you, and various other researchers are also there. You can see their work if you want to explore in this direction. Okay, and these are my reference materials or books, that also you can explore my YouTube channel. There also I have posted various uh, optimization techniques and related videos in exact case, in fuzzy case, and other mathematical tools which have been explained in a very simple way so that your understanding will be simple and it makes a big difference. So that's it from my side.